Okay, well, I guess we'll get started. Thank you, everyone, for joining us for our first combined Parsl and funcX Fest. So Dan and Ian are going to give the introduction. Dan, I'll hand it over to you.
Okay, thanks. Just want to start off by saying that Parsl and funcX have a code of conduct. And there's not really anything surprising there, but we are going to follow the code of conduct in this meeting. It's not just for the online community, but also any kind of meetings that we have. So again, I don't think that there's really anything strange here or unusual, but please be conscious of what you're saying and act constructively. And if anybody has any problems or they see anything that they want to call out, I guess it says on the slide to let me know. So I guess that would be what the action would be. I'm not quite sure, Kyle, why we said me, but okay. All right, let's go on.
You won that lottery. Dan, you might want to give a quick introduction as well so people know who you are.
Oh, sure. Yeah, so, okay. So when we started Parsl, I think Mike Wild, who's on, was the PI of it, and a number of us were co-PIs, including myself, now at University of Illinois. And for funcX, Ian is the PI who will be speaking next, and Kyle and I are co-PIs. So I think we've over, I don't know, a number of years built a collaboration between Chicago and Oregon and Illinois, and I'm the kind of the Illinois center of this, I guess. Should we go on? Okay. This is, so as Kyle was saying, this is the third Parsl Fest meeting that we've had and the first funcX meeting we've had. We think that it's pretty important to have such meetings to bring people together, to let people share what they're doing. And in particular, we've decided to bring these two things together because Parsl and funcX really are interrelated in a number of ways. They're becoming interdependent. They're sharing code. They're sharing funding, sharing staff, and sharing user communities. And they really work together to address different use cases, or there are use cases where you can use both of them together. And so because of that, we thought it would be useful to make sure that people that are using one really get awareness of the other, and also from our view as staff, to make sure that we're using the right tool in the right place and using the right combination of tools when that makes sense. One more. Okay, there are lots of us that are part of the team. I don't know. I don't think we actually have time to introduce everybody here in the few minutes that we're using for introductions, but I'll just say that majority of us will be on for much of the meeting, and hopefully as we're talking and you're seeing us in the participant list, you will see people who are part of the project, as well as people who are users, as well as people that are kind of in the middle that are users but are also contributing. Okay, go on. Okay, and I'll turn it over to Ian at this point.
Okay, hi. Hi, everyone. And thanks for joining early in the morning or late at night in the case of Zhuzhou. So I just get to say a few words before we get on to the much more interesting talks. So we're fortunate to have recruited quite a few people into the Parsl and funcX projects who each bring their own interests, capabilities, and also funding. And so you'll be hearing from various of these groups, but we list here the NSF funding awards that are supporting the work that they're doing. So UChicago and UIUC, you've already heard about from Dan in the case of Parsl, and also funcX, but there are also funding awards to places like Notre Dame and Colorado State, Northern Arizona, College of New Jersey that support us. And then at Argonne National Lab, we've got a growing number of application projects where people are applying the technologies in different areas, particularly relating to cosmology and AI-based experiment steering. and that is supporting additional work relating to here, to what we're talking about here. So thanks very much to both the National Science Foundation and the US Department of Energy for their support of this work. Next slide, I guess. So it's always nice to see these exponential curves. I think at least the one on the left is. The other one perhaps is more linear, but it's always good to see growth. With Parsl, we started in 2017 and continued growth in downloads, visitors, and contributors. So please recruit more people so that we can continue to see this growth. It's pretty astonishing, I think, 400,000 PyPy downloads over this period. And then I assume the one on the right is funcX, and there we've got an interesting set of metrics because it's a hosted service. We can measure not just users, but also the number of connected endpoints, the number of functions executed, and the number of tasks performed. And as you can see, they're all growing substantially as well. So that's very exciting and gives us much motivation to continue the work we're reporting here. I think there may be one more slide. Right, so this is a very informal meeting. We hope to see lots of Q&A. The goal is to, well, let external people learn about Parsl and funcX, what they're being used for, where they're going. It's for Parsl and funcX people to report on what they're doing, to meet the community, share experiences. We emphasize that both these projects are very much open source communities, community driven, enabled by the work of many contributors throughout the community. So we hope that people are here to learn how best to contribute to Parsl and funcX, and to help us understand how best to engage with those who are part of the Parsl and funcX community, external to Chicago, Illinois, and the other core institutions. And so we very much welcome feedback. What are the development activities that are most important to you? What are the shortcomings, the ones that perhaps you think only bother you, but perhaps also bother others? We'd like to know. And we hope to form some new collaborations. A lot of progress on Parsl and funcX has been made possible by people coming together, wanting to do something that seemed crazy or difficult or just interesting, and then going ahead and doing it. I'm looking at you, Eric, Jonas, both of you, with your crazy things that you keep trying to do with funcX. But of course, there are others as well that are pushing us in interesting directions. Anyway, so we're all looking forward to the meeting. Thanks very much for joining. And I think I can now hand things back to Kyle to take things away.
Thank you, Ian. Yeah, I just wanted to reiterate that. Thank you, everyone, for joining us this morning. And big thank you, not only to the teams that have developed Parsl and funcX, but to the contributors that have come and fixed bugs and created issues for us and engaged on Slack. I mean, we wouldn't have funcX, I think, without the community of Parsl users that really led us to that being an important sort of direction to try and overcome some of the hurdles that users faced. Just quickly on the agenda. So we have a fairly packed agenda because we keep adding talks. So we've ended up maybe a little bit more talks than we perhaps expected. And I even note that this agenda hasn't been updated to reflect that. If you look on either of the Parsl or the funcX websites, you'll find an updated agenda. This morning, we'll have 4 hours. We'll have 2 sessions of technical lightning talks or science lightning talks, cyber infrastructure lightning talks, with a couple of tech talks sprinkled in from Jiao and the Parallel Works guys and Kerr. And then tomorrow afternoon, we'll do much of the same again. You might notice that there is almost no themes to this individual sessions, and that is mostly because we scheduled around availability. So we've intermixed Parsl and funcX, we've intermixed science-focused talks from cyber infrastructure talks. I think the good thing is they're short talks, so we get lots of exposure to interesting things. And so if something is potentially not interesting to you, I would suggest in 10 minutes time, the next talk will hopefully be interesting as well. Okay, so I'm as expected, already over time. Ben, Clifford, can you give me a yell when my time runs out in 16 minutes from now, because I don't want to cut into everyone else's talks.
Yep.
Okay, so I wanted to give a quick introduction to Parsl and funcX individually, and the reason for doing so is I think we have two communities here of users with Parsl and funcX, and there is some overlap, but some people are really only exposed to one and some only to the other. So I thought it would be worth a recap of what each one's doing, and then at the end, I tried to come up with a sort of guidelines for when you should use funcX and when you should use Parsl. It's not 100% clear, the separation, but there's certainly some categories of use that fit one or other model a little bit better. So we started this work, as Dan said, about 5 years ago, building on probably a decade or more experience of working on the Swift parallel scripting library. And when we started looking at where we were, we got some NSF funding to try and reach the sort of evolving science community. We stepped back and we looked at, well, how is scientific software developed today? And we noticed a few things. So the first is that a lot of science software really is assembled. So there's a lot of building blocks that people want to combine together to actually address their use cases, to try and perform their analysis or create their simulation. The second thing we noticed, which is no surprise, is I guess with the slowing of sequential processing power, that people are becoming more parallel and distributed in their computing. Nodes are becoming fatter with more cores. A greater variety of users are now jumping onto clusters and other distributed computing platforms. And there's some significant barriers, I think, that make it difficult for people to embrace those types of hardware or those types of systems. And then the third one, I think, again, probably no surprise to the community here, that Python has become fairly common, perhaps the de facto standard language environment for a lot of the science we work with. We're probably a little biased because that's what we see in terms of the people we work with. But I think it's just becoming even more so over time. So it's very rare now that we interact with a new science group and they don't have at least some of their stack written in Python. And the advantage there, of course, is not just that their codes are being moved to Python, but there's a whole ecosystem of support around the libraries, the machine learning libraries, the visualization libraries, etc. So in terms of what we did, we started building up this Parsl library, which aims to basically make it very easy to express parallelism in Python and then to be able to realize that parallelism on different back-end computing systems. And then funcX, we developed a new system where we sort of cut off some of those Parsl pieces and tried to provide a Globus-like abstraction where you have this fire and forget computation model where there's a cloud service helping to mediate some of the more challenging aspects of remote computation. So the one slide sort of review of what Parsl is. So Parsl simply is a parallel programming library for Python. It's written in Python. You can pip install it. You can conda install it. It's all in user space. You don't need any databases or crazy dependencies. So I think in general, it's fairly easy to set up in different systems. We have this model of connecting what we call apps, where apps are these composable units that you're basically integrating into your analysis or pipeline or workflow. And you see on the right here, we have a couple of these app building blocks, a Python app, which as the name suggests, wraps a function or a pure piece of Python code, and then a bash app that wraps calling anything else, right? So anything like an application written in another language, a binary, a script, the gluey sort of stuff that you might have in your workflow. Parsl is 100% asynchronous. So when you call one of these apps, what you get back is a future, which is a proxy for the result. We don't know when or where that app might actually be executed, but by having this future in your code, you can carry on with your control logic. You can pass that future around to other apps, creating this sort of very nice dynamic dependency graph that's assembled over time. So we have what we think is a fairly natural way of expressing parallelism, in that you're basically just invoking these functions in your pure Python code, you're getting back futures, you're managing these futures, and they're only ever being materialized, or you're only ever waiting for the result to actually be performed when you absolutely need it. So when you get to that point in the DAG where you can't progress any further without the results of the previous functions executing. And then the big thing we've focused on in Parsl is to try and make the programs independent of where they're executed. So we really want to focus on portability. It seems like a completely crazy situation that scientists have to spend a ton of time getting a program working on one system to then have to come and spend a ton of time again when they get an allocation on another system. So we've tried very hard to abstract both the systems on which you execute and also the mechanisms by which you execute, the types of model you use for execution. I'll talk about that in a minute, assuming I have time. So an example of a Parsl program or workflow, this is the modus example, which is a common sort of canonical exemplar sort of story for workflows. You see here how DAGs are basically represented. You have some input imaging data. It gets passed through a bunch of different steps. You see here illustrated with the different colors, and each of those steps is invoked one or many more times, illustrated again by the little boxes. And you see this DAG starting to be assembled, where we call out something in parallel, the land use and colorize apps, and then the analyze app needs to wait for the results of those two previous apps to actually be finished. And you'll see in this Parsl funcX Fest meeting a lot of examples of DAGs like this that are implemented in Parsl. So what does Parsl do under the covers? So Parsl basically takes this script or this Python program and turns it into a DAG. We use the word dynamic DAG often when we talk about Parsl, and the reason we say it's dynamic is that unlike some other workflow systems where you sort of have to basically compile your program into a DAG and then you execute your DAG, we try and do both of those things at the same time. The advantage being that we can go and run some things on Amazon or some Exceed resource or a DOE resource, and we can get the results back and complete that DAG as we're going. So we can sort of overlap those two things, and we can try and adapt the DAG as we go based on the actual results that we're getting from the previous apps. So you see here the blue and the pink apps got executed on Amazon, results are returned, and then the green and the purple apps go and execute on an Exceed resource or another Amazon resource and complete the DAG. As I mentioned before, we've tried to enable portable execution of Parsl scripts. We've also tried to embrace common interfaces for the different layers. So this is maybe a bit of a confusing picture when you first look at it. But the way Parsl's architected is we have this Parsl box up the top. I think people can see my mouse, that has the sort of control logic for building out this DAG, managing the execution of the DAG, doing the other fun stuff like moving data around or checkpointing things. Basically, that is your Parsl program there. When you come to run a Parsl program, you select an executor and you select a provider to run that program. The provider basically abstracts the infrastructure on which that program will be executed. So it might be executed on your local system, which I didn't include here as a provider. It was a bit of an oversight. Or it might be executed on a cluster using Slurm or LSF, or it might be executed on a cloud like Amazon Web Services or Google Cloud. And so we have an abstraction, an interface here for plugging in different backend providers. The other thing we have is an abstraction for managing the execution of those tasks. So essentially, you can think of a Parsl program when you process that DAG as just being a queue of tasks that need to be executed. And we don't really care how those tasks are executed. There might be different sort of requirements on how those tasks are executed. There might be lots of them that execute very quickly. There might be few of them that execute more slowly. And so you might have different requirements for how those things are executed. And so what we've done is we've implemented the Python concurrent futures executor interface here, which basically takes a stream of tasks and is responsible for executing them and filling in the future when the task is completed. We built a few of our own executors, indicated here with HTEX, the high throughput executor, XX, the extreme scale executor, and originally we also used the IPy parallel executor. Over time, one thing that I think has been really encouraging about this sort of approach has been that we've been able to plug in different executors, such as the funcX executor, you'll hear about this at this meeting, the WorkQ executor from Notre Dame, Radical Cyber Tools, and even a few others. And so what this allows us to do is exploit this infrastructure that people are already familiar with or that provides particular benefits to the types of applications they're executing. I should also say as well that these executors are in different states. So the left two here, the HTEX and WorkQ executors, we consider production. These are the two executors most people use. The next four, Flux, XX, Radical, and funcX, are prototype executors, and you'll hear about these today. Our hope, of course, is to keep working on these and turn them into green. And then the red one, IPy parallel executor that we no longer use because essentially all of the capabilities we've now been replaced with HTEX. We've done some performance testing. As you all know, Parsl scales relatively well on fairly large. This is on Blue Waters on what, up to 8,000 nodes here. We've seen HTEX scale easily to 4,000 nodes, the capacity of Theta, and running at the capacity of Cori as well. Okay, so I'm about halfway through my time, and now I'll switch tack to funcX. So where did funcX come from? So there were a few observations that we had from using Parsl ourselves and from our user community using Parsl. And there were a few sort of common use cases that we kept sort of running into challenges with. So the first is a lot of people would like to use Parsl, say, from their laptop to manage a remote or even a multi-site computation across multiple nodes. And it turns out while Parsl supports that using SSH channels or SSH connections, that can still be quite problematic, right? You need to keep a persistent process alive. You need to have the ability to dial back in to that Parsl process running on your laptop, which in many cases is not possible. SSH connections, of course, are quite fragile, and the sort of ubiquitous deployment of 2FA makes authentication fairly challenging as well. A second thing we noticed is a lot of Parsl programs actually have few or sometimes even no dependencies, right? So a lot of Parsl programs really are bag of tasks, and what a user would like to do is just say, I want this bag of stuff executed. I don't care when, I don't care where, I just want it executed. I want someone to manage it for me. And so using a Parsl program to do that is possible, but it requires a little bit of hand holding from the user. And then the third thing we noticed, and I think this is very familiar to all workflow developers, is that configuring Parsl for different systems can be and is complicated, not just from the perspective of different systems have different schedulers that all look completely different for some reason, but also from even deployments of the same scheduler on different systems look different, through to systems tend to change the way that their schedulers work, and a configuration that worked a year ago or a week ago might not work tomorrow. And so we turned our attention to thinking about, can we build a simpler model for running these remote tasks? Can we look at the way that cloud hosted services have been developed? Can we look at the success of the Globus service for managing data and try and bring that to a computation model? And so this is where funcX came from. funcX, very briefly, is a cloud hosted service that offers fire and forget function execution. You can register and share basically a function execution endpoint. So you deploy that on a system, and then you can share it or use it yourself or share it with your friends. Users can register and share functions in the cloud. So this is basically the Parsl app. You can register those for all time in the cloud, and then you can invoke it later. You can share it with someone else to invoke. And what this allows us to do is provide reliable, scalable, secure function execution on remote endpoints. So I see I'm down to 4 minutes, Ben, I'll hurry up. So funcX is comprised of these two pieces. The funcX agent, which is the endpoint software that's deployed on the system you want to use. Again, 100% Python, so you can pip install that, conda install it. You see on the right, basically the steps you need to go through. Pip install the endpoint, configure the endpoint, start the endpoint. Once that's started, you've got a UUID, you can start routing tasks to it. We use Parsl. This is basically servicifying the bottom two layers of that Parsl diagram I showed before, the provider and the executor interface. Manages concurrent execution on the same resources Parsl supports. You can optionally use containers, and you can share these endpoints with other people so that multiple people don't need to go through the pain of setting things up. When you come to actually use this and you want to execute some work on that endpoint, the first thing you need to do, and sorry for the quality of the slide, you need to register a function. And this again looks sort of like Parsl. We define a pure Python function, and we just pass it through our SDK through the register function command. We get back a UUID, and now we can invoke that thing. So complete access control on that function. When it's created, it's only accessible to you, but you can make it accessible to other people. When you want to then go and invoke it, essentially it's just passing in a pair. You pass in the endpoint ID you want to use, the function ID you want to invoke, and then any Python arguments you might want to pass to it. You get back an asynchronous result. So we have an executor interface with a future, or there's a UUID that you can use for that result. We'll store that result in the cloud. We'll try our best to execute it. So if your endpoint's offline, we'll queue it, and we'll keep trying to execute that thing until it can actually succeed. We keep the results in the cloud. Someone will have to tell me exactly how long. I think at the moment, about 30 minutes or an hour, but we're moving to a model where we'll be able to keep results in the cloud even a little bit longer than that, upward of a week. We've done similar performance analysis of funcX on Theta and Cori. I think the key point here is that we scale relatively well up to 2,000 concurrent containers. We can scale much further, but if you're running very short tasks, then the overheads will become a little bit problematic. So we're working to improve this performance, but at the moment, this is sort of what the performance looks like for funcX. I have 1 second to explain this side. You're going to probably hear a few talks. Well, definitely you're going to hear a few talks today about using funcX in automated research lifecycles. So we have another system that we're not talking too much about today, another CSSI funded system called Globus Automate. This basically allows people to define sort of workflows that span space and time, much larger latencies than the Parsl workflow system. So it's not workflows for managing like tightly coupled tasks on a supercomputer or HPC system or cloud. It's a workflow system for linking together different actions, where actions might be ask a user to approve something. It might be transfer some data between here and there. It might be enter some metadata. It might be run a funcX function. And so you'll see that funcX ties very nicely to this Automate platform. And a few of the talks today, especially around instrument science, you'll hear a lot about that. Okay, so I've got 1 minute left. This is my quick effort at separating Parsl and funcX in terms of where one might fit better than the other. So if you have a workflow, you're running on a single site, you're really focused on very high performance, extreme scale, you have some MPI apps potentially in your workflow, and you want to use fairly varied wide area data management, what would be the right word, actions or capabilities, then Parsl would be the right fit. For funcX, if you have a bag of tasks, or you want to run across one or more sites remotely, you want the fire and forget execution model, you'd like to run in containers, you want to be able to share stuff amongst a community or amongst a group of users, or you want to plug into this automated event-based model with the Globus Automate platform, then I think funcX would be probably the best bet. But we're increasingly starting to think about Parsl and funcX together, and Georgia will give a talk of our initial work here to combine the two systems. And our hope there is that we'll be able to get sort of the superset of these two set of characteristics in that implementation of Parsl and funcX. So if you want to implement a workflow that is executed reliably, it spans sites, or at least executes on a remote system, then the Parsl plus funcX integration would, I think, be a good fit. Okay, so back to the agenda, which, as I said, is outdated. We've added an extra 15 minutes today, and we've crammed another couple of talks in tomorrow, but we'll still finish by 5. I'll hand it over to Ben Clifford now, who's going to introduce the first session.